Okay, so now we're going to get into a discussion of quantum numbers and atomic orbitals, and this comes out of the calculations done by Schrödinger, because if you remember, we said that the solution to the Schrödinger equation are what we call wave functions. And in order for us to get those wave functions, those wave functions must have three parameters that we call quantum numbers. And these numbers are integers, all right? But there are certain rules that we have to look at and obey in order to determine what these quantum numbers are. Now, any wave function with a given set of these quantum numbers, we call that an atomic orbital, all right? And these orbitals basically occupy three-dimensional space and gives a picture as to the region in which there's a probability of finding an electron being very high. And when I say high, I mean above 90%, all right? So we're going to look at these quantum numbers, the first of which is known as a principal quantum number, which is signified by the lowercase n. And basically, it is firstly independent of the other quantum numbers that we're going to discuss. Now, n can only be a positive integer starting from 1, all right? So that's basically what n is. And in fact, I should mention that this n here corresponds to the n values that we saw in the Bohr model, all right? So there's some correspondence between the Bohr model and what we're talking about here, but again, we have to recognize that the Bohr model fails for the reason of Heisenberg uncertainty principle, which says that basically in the case of the Bohr model, you cannot find or you cannot tell that the electrons will be traveling in well-defined orbits. The size of an orbital and its electron energy is dependent on the n number. So basically, the greater the n value, the greater would be the size of the orbital, and the higher would be the energy of that particular orbital. And then you can have situations where orbitals will have the same n value, and therefore they're said to be in the same shell or energy level. So if you hear me use the term shell, it means the same thing as energy level. And I'll be using those two terms interchangeably when discussing the principal quantum number, all right? So that's what the principal quantum number is all about. Now, the next quantum number is known as the orbital angular momentum quantum number, symbolized by the letter L. And this actually determines the shape of the orbital, right? And there's some designation, letter designation that's associated with the L values. So if L is equal to 0, we're referring to what we call an s orbital. If L is equal, or s sublevel, I should say, if L is equal to 1, that is referring to a p sublevel. If L is equal to 2, that's a d sublevel. And if L is equal to 3, then that represents a s sublevel. So these basically represent different sublevels within the energy levels, all right? Okay, so in terms of the actual values of L, the only possible values of L will range from 0 to n minus 1, where n, of course, is the principal quantum number that we met before. So let's say we're talking about the second shell, where n is equal to 2. That means that there are only two values possible for L, and that would be 0 or 1. And what that means basically is that within the n equal to shell, there are two sublevels or subshells, one where L is equal to 0, and the other one where L is equal to 1, all right? And I can extend this further just to use another example. So let me do this here. So let's say if L is equal to, hold on. So let's say if n is equal to 3. So let me write down here, n equals 3. If n is equal to 3, then the possible values of L would be 2, 1, 0, right? So what this means is that in the third shell, you have three subshells. You have the L equals 2 subshell, L equal 1, and then equals 0. 0 would represent the S subshell, 1 would represent the P subshell, and 2 would represent the D subshell, all right? So that's basically what the L value is all about. Okay, so let me go back to this slide right here. Okay, now each of these orbitals is a different region in space and have a different shapes, right? And all orbitals having the same value of n and L are said to be in the same subshell, which is what I was referring to before, all right? So basically all orbitals that belong to, let's say, L equals 0 Well, that means that they belong to the same subshell. And for L equal 1, for the same shell, those orbitals belong to the same subshell. All right? Now, the next quantum number we're going to talk about actually gives you information about the number of orbitals that are present within a subshell, and that's called the magnetic quantum number. And in actual fact, this magnetic quantum number determines basically the three-dimensional orientation of the orbital in space. And the possible values of ml is dependent on the value of L for the subshell. So for example, if L is equal to 2, then the possible values of ml would be, well, let me just say this first. Possible values would go from minus L to plus L, all right? So if L is equal to 2, then the possible values of ml would be minus 2, minus 1, 0, 1, and 2. So the way we would interpret this is that in the L equal 2 subshell, there are actually 5 orbitals. Each of these numbers represent a particular orbital within the L equals 2 subshell, right? So basically within any subshell that has a value of L equal 2, you know that there are 5 orbitals present within that subshell. And just to give you another example, let me get out of this here and go back to this right here. If, let's say, okay, so let's say, let me draw a line here to make a distinction. So let's say if, okay, where am I? If L is equal to 2, then the possible values of ml would be equal to plus 2, which is plus L. Then, no, we did that already, I'm sorry. If L is equal to 1, then the possible values of ml would be plus 1, 0, minus 1. So therefore what that tells you is that for L equal 1, which represents the p subshell, there are 3 p orbitals present, right? So there are 3 p orbitals present because each of these ml values represent a p orbital, all right? So that's how we interpret the ml values. The number of ml values actually gives you the number of orbitals present within a particular subshell. Okay, so let me get out of this and go back to the PowerPoint slide. Okay, so we have dealt with, so far, 3 types of quantum numbers, but there's also a 4th one, which we'll talk about later on. But before we do that, I just want to show you this summary of what we just discussed so far. So basically, we talked about the principal quantum number, which is n. For the first shell, n is equal to 1. For the second shell, n is equal to 2, and so on, right? For the L value, the possible values of L would be equal to n minus 1 to 0. So for n equal 1, there's only one possible value of L, which is 0. So that is true for the first shell. For the second shell, there are 2 possible values of L, which would be 0 and 1. For the third shell, there are 3 possible values of L, which would be 0, 1, and 2. All right? Then we get to the ml values, which is dependent on the L values. Remember, ml is equal to plus L through to minus L. So if L is equal to 0, then there's only one possible value for ml, and that would be 0 here, and also here for the second shell. But when you get to the L equal 1 possibilities, there are 3 values of ml, minus 1, 0, plus 1. So what that tells you is that there are 3 p orbitals present, right? Or 3 orbitals present within the L equal 1 subshell. And then over here, we have the same thing here and here for L equals 0 and L equal 1. But when L is equal to 2, then the number of L values would be 5 of them, from minus 2 to plus 2. So down here you have a summary of the different numbers of orbitals of each type that is present within each subshell. And a pattern emerges where you can recognize that where s orbitals appear in any particular shell, they appear singly, right? So there's only one s orbital that will exist in any shell. As far as p orbitals are concerned, there are 3 of them that will exist. So as you can see, there are 2p orbitals here. The 2 here indicates that they come from the second shell, and there are 3p orbitals here, right? The 3, of course, indicate that these p orbitals are within the third shell. And then when it comes to the d orbitals, they appear in sets of 5s, all right? So that's the pattern that emerges when it comes to the different orbitals. And we're going to see that there's some higher energy orbitals later on. Okay, in terms of the actual shapes of these orbitals, what you'll find is that the shape is, of course, dependent on the wave function. And if you plot the square of the wave function versus the distance of the electrons away from the atom, you'll get a curve like this. Now, I think, if I'm not mistaken, this is for the first shell, where n is equal to 1. And of course, what you'll find is that the probability of finding the electron decreases, because that's what psi squared means, right? This is the wave function squared. That's the probability of finding the electron decreases as you go away from the nucleus, which makes sense because the electrons are negatively charged and the nucleus is positively charged. So therefore, the electrons will most likely spend most of its time around the nucleus. Now, what is used to actually determine the shape of the orbital is this plot right here. 4 pi r squared times the wave function plotted on the y-axis versus r, which is on the x-axis. And that gives you the probability of finding the electron within a particular volume of sphere of a radius r. All right, so that is a more accurate representation in terms of giving the actual shape of the orbital. So the conclusion of all of that is to say that when it comes to s orbitals, and more specifically the 1s orbital, it will look like, as it says here, a fuzzy ball, right? So this is a spherical shape associated with the s orbital, right? So this is a plot. When you plot the volume times the wave function, well, not a volume, but a region representing the volume times the wave function against the distance, you're going to get this plot right here. And in terms of a picture of how the electrons are, the probability of finding an electron is within that region, we have this representation here. You can imagine this as being representing different snapshots of the electron in the atom, right? So if you take a picture of an electron at one point and then at another point, and you just repeatedly do that, that's a picture that you're going to end up with when you overlay the different pictures of the electron in this particular orbital. So that's the 1s orbital. The shape of the 1s orbital is spherical. And it turns out that when it comes to the next orbital in a higher energy shell, it has the same shape with one exception, and that is that there is a region here which is called a node, right? The node is basically a region where the probability of finding the electron is 0, right? And that comes directly from the plot that you'll observe right here, all right? So what you'll find is that as you go into higher energy orbitals where you have s orbitals, the number of nodes increases. So for the 3s orbital, it's going to have 2 nodes. For the 4s orbital, it's going to have 3 nodes, and so on. Then we get to the p orbitals, and it turns out that the p orbital is shaped like this. Now remember, we said that the p orbital, they come in sets of 3s, and it turns out that in terms of their 3-dimensional arrangement, they are arranged at mutual right angles. So if you can imagine, and this is something you probably should be familiar with, the 3-dimensional Cartesian system, where you have the x, y, and z axes perpendicular to each other, then what you'll find is that the arrangement of the p orbitals will be where one of them will have its axis along the x orbital, or the x-axis. It will be aligned along the x-axis, this p orbital here. So we call that the px orbital. Then we have this orbital aligned along the y-axis. So it's called the py orbital. And then we have this p orbital aligned along the z-axis, right? So this is basically what they look like separately. Together, this is what they look like, right? So remember, we said that the p orbitals, they always appear in sets of 3s. So it's the same situation for the p orbitals in the second shell, the third shell, the fourth shell. Remember, there are no p orbitals in the first shell because the L value for the orbital or the sublevel within the first shell is 0, and therefore that means that there's only one type of orbital present, and that's s orbital in the first shell. Then we get to the d orbitals, and as you can see, it's even more complex. I won't expect you to memorize these shapes. All you need to know is that d orbitals, they appear in sets of 5s. So these are the 5 d orbitals. This is what they look like separately, and this is what they look like together, all right? So that's basically what the d orbitals look like. And I won't go into even the other orbitals. You have the f orbitals, which is even more complex, which I won't get into, and some higher orbitals. You have F, and you have G, and it follows the alphabetical order in terms of the letters. Okay, there's one more quantum number that we need to discuss, and it's called the electron spin quantum number. And this one is the easiest to understand because there are only two possible numbers. Now, the discovery of these numbers is based on the finer features of the atomic emission spectrum, right? And it turns out that when it comes to the electrons in an atom, they tend to, well, their spins are quantized. In other words, there are only two possible spin possibilities for electrons, right? You can have the electron spinning in one direction, which is represented by the arrow shown here, and spinning in the opposite direction, right? So those are the two possible spin directions. Now it turns out that when electrons or when any charges are moving, they generate a magnetic field. This is something that if you did physics or if you're about to do physics, is something that you learn. So in the case of the electron spinning in this direction, it generates a magnetic field going from north to south like this. If the electron is spinning in the opposite direction, then the generated magnetic field will go from north to south going down, right? So basically, when it comes to representing electron spins, we use arrows to represent the direction of the magnetic field that is generated. And the two quantum numbers associated with the different directions is simply plus half and minus half, right? So those are the only two possible spin quantum numbers that exist when it comes to the electrons. Ms is equal to plus half and ms is equal to minus half. And these numbers are in no way dependent on the other quantum numbers that we talked about, which would be the principal quantum number, the magnetic L value, and the ML value, all right? And the next slide shows you the experiment. I won't even go into this, but this is basically the experiment that led to the discovery of those spin quantum numbers, all right? The Stern-Gerlach experiment. If you want to read up on that, feel free to do so. Okay, so that's basically it as far as this chapter is concerned. So the next chapter will be, of course, chapter 8. And here is where we're going to look at how the electrons are distributed in atoms and other related topics. All right? Okay, so until then.